Tak vypadá to, že by to mohlo běžet. Doufám, že online nás někdo slyší. Ano, já slyším sám sebe, je to pořád, funguje, hraje. Tak, vítám vás na 38. TechMeetupu tady v Ostravě a protože máme Adama, spoluorganizátora TechMeetupu, který stojí zde vedle mě. A ten propojuje komunity, tak to dneska máme společnou akci s PyData Prague. Honzou.
A ještě tady někde by měl být jako Kuba.
A s Kubou. A já vám moc děkuji, že jste tady dorazili za náma do Ostravy. Jste připravili přednášky, že to dneska bude v angličtině, což je nová věc, ale než se do angličtiny switchneme, tak kromě dnešní akce, za kterou jsem moc rád, že jste přišli a máme tady nějaké online sledující, tak vás chci pozvat právě za 14 dnů, 30. ve čtvrtek bude v hospůdce jménem Palouk, Data Circle, který se zaměřuje právě tady na ty témata, které se tady budou dneska probírat. Nemá dopředu daný program, každý přijde s něčím, co chce vyřešit a vzájemně se o tom bavíme. A 7. listopadu v pátek bude velká TechMeetup konference tady v Ostravě. Najdete cokoliv na techmeetup.cz nebo na meetup.com a budeme moc rádi, když přijdete. A předávám slovo.
Dobře, no teď bude strašně těžký přijít do té angličtiny. Okay, so welcome everyone. We are very glad that we could come to Ostrava thanks to TechMeetup. And so let's have fun having this joint event. And we will have a very short introduction about what PyData is and why we came here. Oh, maybe I don't know why we came here, so I will skip this point, but I will speak about what PyData is, and then we will have 4 nice, interesting talks. That's why we came, actually. So we will have 4 nice talks and a lot of refreshments in between and afterwards. So thanks, TechMeetup, and also thanks, Impact Hub, for hosting us. So the schedule I already mentioned that there will be 2 blocks of talks. Hopefully we will end with the talks at 2020, then we will skip back 5 minutes in time, and then we will, okay, so please don't follow, we will not follow this schedule too strictly, and that is important. We will, of course, it's a small community here, so you can ask the speakers directly after the talk, but you can also post your questions on Slido. Just visit sly.do and enter this hashtag, or you can scan the QR code. There is one important thing here. We will select the question that has the highest number of upvotes, and that person who posts this question will get a free ticket to TechMeetup conference, which Matěj already announced, which will take place on 7th of November. So now you have motivation to properly ask. And I guess that's also like also for the people who are online, they can also ask, is that true? Yeah, I mean, why not? So enough time to scan the code, and now I can. What is PyData actually? Not just PyData Prague, but the whole PyData thing. So PyData is an educational program by NumFocus, where NumFocus is an American NGO that helps this educational and communities like PyData, but they also sponsor or help maintain some of the most important scientific and data Python projects. So if you know NumPy, Pandas, Matplotlib, like 40 others, you name it, you probably, there is some indirect or direct link to NumFocus. So PyData itself is composed of many groups worldwide, like ours, but there are 200 of those worldwide, and they organize both meetups like ours, but also larger conferences like, I don't know, PyData London, PyData Berlin. These are quite huge conferences, actually. And these numbers are misleading, so we can skip them happily and go to what PyData Prague is. So our series of meetups was established in 2018, and up till today, every event took place in Prague or online, but this is the first other city than Prague we actually have a meetup in. And okay, another misleading number, 2,000 members on meetup.com. 5 volunteers behind the scenes. That number is definitely not misleading because it's a completely volunteer project. We do it in our free time. And just to name the people, Jakub, who is sitting there, okay, me, then Erika, who is our marketing guru, Jirka, and Adam. And we do these meetups, but we also do some other things. So we helped organizing PyCon CZ, and we also created a course for PyLadies, which is targeting the data. And yeah, 31 meetups so far, including this one. If you wanted to know what the previous talks were about, most of them are recorded and publicly available on YouTube. So if you Google YouTube and PyData Prague, you'll get to a collection of, I don't know, like 50 talks or something like that already there. And we are also recording this one, both as TechMeetup, and also we will put the talks later on YouTube. One important thing, a code of conduct. We have to repeat it every time, but luckily with PyData, we didn't have any issue yet. And just be kind to other people, be professional, respectful, etc. And we also, it's not just about the organizers, the volunteers. It's not only about the speakers, while they are somewhat important. It's also about you who are sitting here. So please participate by socializing, sharing the knowledge among you. Keep coming. I mean, that's a bit more difficult if you want to come to PyData Prague, but definitely Praha is not so far away from here. And we manage, so you can also manage. You can follow us on the socials. We have Blue Sky, Facebook, and LinkedIn, but most relevant information is always posted on meetup.com, which is the first place where we announce our events, and all important and up-to-date information is on meetup.com. We like people preparing talks. So if you feel like giving a talk at one of our meetups, it will be fine. And if you need to somehow compensate the travel from Ostrava to Prague, we can arrange that. And ask your employer to sponsor a venue. Maybe that's more targeted to Prague, but maybe we come here again, and also we can find a venue in Ostrava. And I think I'm speaking for too long. So with that, I will go back to Slido and while speaking about that, I would like to invite our first speaker, who is Darius, who will kill the Gil. And I just want Matěj to prepare him for that technically.
Take maybe 1 minute to switch it and share also online. I will also give you the microphone. So, give you a microphone. Yes, and will you?
I will ask the questions maybe later. So,
Later, yes.
So just take it.
A mám teda začít shareovat, jo?
Napřed to nasdílej.
To share.
Máš a teď dej share a dej celou screenu.
Okay.
No.
Tady
No, já myslím, že právě ono, že si překliknul, jo.
Na pohodě. Teď si to zvětš.
Dám někam pryč, tady to zapnu.
Tam bylo nějaký malý. Jo, už jsem
Dobré. Tak můžu začít? So, hello everyone. I'm glad to be here. My name is Darek. I work at Atacama as software engineer in AI team. And for today, I prepared a presentation about something that I think is maybe one of the most exciting new additions to Python in the recent years, at least according to my Twitter feed or X feed. If you are in the same algorithm as I am, you've noticed some pretty high reactions towards the new Python release, especially to the fact that in the new Python version you can disable GIL. So some folks were pretty hyped about that. I like this last tweet that it's after this last release, it's actually harder to make fun of us. So we will see if it's true, and what does it mean? Let's talk about that, right? So let's talk about what is GIL, why GIL was added to Python, how we can disable it, why you might want to disable it in your projects. We will go through some benchmarks, and we will wrap it up with some, let's say, conclusion. Okay, so let's start with why GIL exists. So GIL, as some of you know, stands for Global Interpret Lock. And in the last several years, it has had this, let's say, bad reputation, bad name, bad rep, that it limits performance of Python applications. It limits parallelism in Python applications. So why it was added in the first place, especially when you consider that it has been part of Python for over 33 years, right? So couldn't they just remove it or improve it? Why they added it in the first place? So in order to answer the question, we need to go back in time. And don't worry, I will be quick with this history lesson. So in 1991, Python was released, or like the major version, and just a year after that, GIL was added together with support for threads. And that's quite interesting because those two things, they were released together, and it's not a coincidence. They added it together, they released it because when you have threads, and when you have threads which share, for example, some memory together, you have a risk of race conditions and data corruptions. And the shared thing that they wanted to protect was reference counter. So how Python manages memory is that it tracks references to your variables, right? And when you, for example, have a variable and that variable doesn't have any reference to it, it signals to the interpret, or interpret knows that it can safely free up the memory and use it for something else, right? So if you have race conditions and other corruptions, what you end up with can be memory leak, right? So they wanted to avoid that. And some of you may have a question. So did they bother about parallelism in Python back then? And the simple question is no, they didn't bother at all for two main reasons. One of it is threads were like very immature back then. It was 3 years after the introduction of GIL when the standard for threads was introduced. So that was like a first thing. And the second one, even bigger one, is that they couldn't run anything in parallel back then, because in order to run something in parallel, you need multiple CPUs. You need two CPUs with multiple cores, and they weren't available back then. So it was almost after a decade after the GIL release that we can see first, let's say, multi-core processors. So, for example, IBM released in 2001 first dual-core processor, and 4 years after that, Intel and AMD, they introduced their versions of multi-core architectures, and then with every year, new CPUs with more cores, more power were released. So, for example, my laptop has something like 14 cores. So, and that brings me to GIL and why it has such a bad rep nowadays, because after introduction of those CPUs with multiple architectures, there was some demand for parallelism, and what GIL does is that it limits everything basically to run only on one single CPU core at a time. Sometimes you hear that what GIL does is that it limits the execution only to one CPU thread, CPU core, which is not true. The important fact is that it limits to one CPU core at a time. I think it's much you can understand it much better from this animation. So as you can see, we have 3 threads, let's say running on 3 CPU cores, or not running. It depends, right? I hope that it will catch the signal again. Maybe not.
Maybe this will be better.
Sorry. Okay, great. So we
share the screen because we do not have it online.
Okay.
Just go to StreamYard and try present.
This
here.
Share screen.
Hello.
Okay.
Yes. And now it should be okay.
Okay, sorry for that. It must have happened. So we have 3 threads, and as you can see, only the green one is actually doing something, while the other 2 have to wait in this idle waiting state to get a chance to acquire the lock and to actually do something. So it's not very effective. I prepared some, let's say, hard evidence so that you don't have to believe only my animations and memes. So I ran some benchmarks. Those numbers, they are very dependent on your laptop. So for example, those benchmarks I run on my second laptop, which has 10 cores. So I prepared this, let's say, simple example where I try to simulate some CPU-bound tasks. So again, it's for the presentation purposes, it's slightly, let's say, dummy artificial example with an increment. So I have a counter, and I try to increment it 1 by 1 up to 100 million. So I'm simulating some CPU-bound, heavy operations. You can replace it by any other CPU-bound task you can think of. I don't know, some simulations, or for example, I don't know, you have trading bot, you would like to run some back tests that you can parallelize, you can run in parallel, right? So when I run that, I get something around 6.5 seconds. So that's like synchronous execution. And some of you might have an idea to run it in parallel, right? As a matter of fact, this is something that we receive very often during, for example, job interviews. Our candidates suggest that very often, that we should run it in parallel, right? So let's try to do that. So I expanded my previous example, and I'm expanding it in such a way that I'm creating threads. In this case, I'm creating 10 threads because I have 10 CPU cores. And I'm taking the value, the 100 million, I'm trying to evenly distribute the workload to those threads. And let's run them in parallel. So as you can see, the execution time got even slightly worse because there is some work related to the threads creation and to pause them, resume them, and so on. So that's not great. What is even worse, we introduced a race condition. So we have a shared value counter, which is mutated with every thread. So because we are professionals, we need to fix that, right? So usually how you fix those things is that you add logs. So in this example, it's the same example. I just edit those few lines where I create a log, and I'm trying to log the value of the counter, which in some sense is similar what interpret tries to do, right? It has also some counter, and it tries to protect the counter from race conditions and data corruptions. So, and when I run this example, the results are even worse, like I don't know, 4 times worse. So that's not ideal. And to summarize it, if you think about it, I had a simple task, right? I have this small, beautiful function, and I just want to improve the performance of that function. And I end up with this and 4 times worse execution time. So we failed. Some of you may argue, okay, that's because of the logs, right? We don't need them. We can create like separate counter for every thread. Okay, so let's update our example. In this example, I'm creating counters for every thread, basically, so that we don't have to touch this shared part of the memory. But even after this update, we got slightly worse result than when we run it synchronously. So as you can see, also from this, let's say, summary, we couldn't beat the synchronous execution in Python, which I find quite sad in 2025. So there was, it wasn't possible for us to basically overcome this limitation. There are some ways how to overcome it. So for example, in 2008, multiprocessing was introduced, right? So this is like a default way for us, I would say, how to do something in parallel and stay in Python. So you create processes. But if you worked with processes before, you must agree with me that the developer experience is not great. So for example, the arguments that you pass to the processes, they need to be pickable. So you need to be sure that they can be serialized and deserialized. They are also copied to the processes. So sometimes you have those weird errors that you, for example, expect that the state of the object will be different, but it was a copy of that object, so the state stayed the same, and so on. So processes not great. There were some attempts to remove or improve GIL. So in 2011, they slightly improved the performance of GIL, and there were some attempts to remove it, but all of them failed. And in 2015, asyncio was added to help us with IO-bound tasks, but it's not effective for CPU-bound tasks. And then I tried to like semi-randomly handpick some events from 2020s to illustrate like the increased push for parallelism, right? So for example, if you have reinforcement learning, you would like to run the gyms in parallel, or ChatGPT increased the whole focus on AI, data processes, and so on. Maybe as a consequence of it, Mojo, which is another language that looks like Python but doesn't have GIL, was introduced. So increased, let's say, demand for parallelism. Also, I copy-pasted some quotes from some of the maintainers and developers of very, very popular Python libraries, such as NumPy, DataFrame, and so on. I like this conclusion. It's from one of the presentations about GIL, which concludes it like, just kill it. Like, we need to do something about it. This is not great. And this challenge was heard out by some great developers, and they started to work on that. So they created this no-GIL branch in 2020. And in 2023, they introduced this proposal to remove the GIL. And a year ago, first version without GIL was released, 3.13t, which was hidden, which had experimental label basically. So when you run this build, you got some warnings that it's experimental and maybe it will be removed in the future and so on. So this release, Python 3.14. They removed this experimental label, so now it's safe to use. Okay, so let's run the same battery of benchmarks again. Now without GIL after 33 years. Okay, so when we run the single-threaded example benchmark, we get very similar execution time as the previous run when we had GIL enabled, which is a huge success because, as I mentioned, some attempts were created to remove GIL in the past, but they all failed because synchronous execution suffered greatly. So it's not the case in this implementation. Okay, so now let's finally run our benchmark for the first time after 30 years in parallel, right? So let's run those threads in parallel. So, so the execution time is actually not great, even with GIL disabled. What is even worse is that when you have those threads running in parallel, you have much higher chance to encounter race conditions. So when you run this, you get every time a different value. So that's definitely not great. So let's add the logs, right, to fix it. So we added the logs, and now this is the great moment. This is what we've been waiting for. So it was horrible when I run it. So when I run it, it took like 3 minutes to calculate it, to compute it. To be honest, on my newest laptop, it's much better, but still it took something like 40 seconds. So that's definitely not great. So when we update this example and remove the logs and shared memory and so, run it again, this is success. Yeah, this is eventually we succeeded, right? So we improved the performance of the application by a lot. So we can say that we succeeded. Finally, we could run something in parallel and improve the performance of the whole application. So this is like a summary. So as you can see, the fastest execution was without GIL, but also without access to the shared memory. So this is like a rule of thumb when to use no-GIL build and when to run it with multiple threads. The conclusion is, and this is the quote from the author of this no-GIL branch, that concurrent modifications simply does not scale well, basically with shared data. So when you have a read, that's okay, but when you mutate this shared part of the memory, it's you need to be aware of those, let's say, penalizations in your performance. So as always, develop but responsibly. So now let's talk about phases. So they want to release it incrementally. So we are in this first phase that we have two builds, basically. One is the standard build, and the second one is one that contains this no-GIL implementation where you can disable GIL. In the next phase, hopefully in the next release, this feature will be implemented, will be in the default release, hidden behind some feature flag, and in the last phase, it will be enabled by default. Okay, I can switch my slides now. Okay, this is how we can try it. I encourage you to try it. So just install Python build that contains this no-GIL implementation. It's in 3.13t. That was like the first version that contained it. You just need to be sure that you are installing the version which has this t suffix. Yeah, and then you can control it by setting up this environment variable, and that's all. So thank you for your time. I hope that it was interesting.
Okay, thank you, Darius. That was very interesting, and it's nice that you were able to kill GIL. And we have quite a few questions on Slido. First one is, hello everyone, just a test. Okay. But then maybe more important questions. What is the penalty if I run a single-threaded app in 3.14t using no-GIL Python, but without using the biggest feature?
Without using the biggest feature.
So probably comparing like 3.14 and 3.14t for the same app.
Okay. There were some significant performance, let's say, improvements. So when I run the same benchmarks using 3.13t, I got worse results by a lot, I think, by almost like 50%. So there were some performance improvements in the newest version. So I recommend using that. Also, when you run 3.13t, you get a lot of those warnings, and it doesn't look very, very good.
Thank you. So maybe time for another question from the audience here. Is anyone willing to publicly ask here, or should I continue with Slido questions?
We often you only want.
Just a moment.
Can you please, like, for the audience to use this mic also?
Often you want to turn the GIL off only for a certain part of your program,
Mhm.
but not always, and you do want that protection. That's partly why you use Python over C++, apart from other reasons. Is there ever a plan, do you know of, to make it so you can turn it on and off at will, or how have you thought about how to tackle that?
I'm not aware of such a plan. I think that at some point they will just remove a possibility to enable GIL, right, at some point. But until then, I think it will be like before you start the application. So, yeah.
Thank you. Okay, next question. What about the compatibility with well-known scientific libraries like NumPy or Pandas? Will they work?
They will work eventually.
Better or worse? Or not now? Or how is that?
So I hope they will work better, but they need to make some critical changes in order to be compatible. So yeah. So for example, I don't know. In my project, I wanted to switch to Python 3.14t, and unfortunately, for example, Tane, which is a caching library, doesn't support that yet, right? Because part of this core implementation of the cache is written in Rust, and they need to make some updates to their code base. So eventually. Yes.
But many of them already are.
Many of them already are. Pydantic, for example.
Okay, that's really probably a simple question. When you are running multiple threads without GIL, will other threads run on different CPU cores?
Yeah, I could check that, but I didn't, so I'm not sure. It's up to the operating system, right? We don't have any, let's say, we can't force it. It's up to the operating system. So what I did is that I ran it several times in order to have like average of those benchmarks.
Okay, so last question from here is, are the mentioned phases of no-GIL development defined in a PEP or somewhere else?
Yeah, they are. So I took it actually from one PEP. They also created some, let's say, requirements, how the implementation of no-GIL, how the implementation must continue in order to be included in the standard implementation. So for example, I remember that one of the points were that synchronous execution can be slower than 10% from the GIL implementation. So that's, for example, one of the requirements.
Okay, so I guess that was our last question. And is there any other question in the audience? If not, then thank you, Darius, again.
Thank you.
And our next speaker is Martina, who is not speaking about dead things, but maybe about live things.
Chceš mikrofon?
No, já myslím, že mám
Tady
tenhle,
to je
ne?
v pohodě, já jenom kdyby se, jako aby všichni slyšeli. Když budeš mluvit trošku nahlas, tak to bude v pohodě.
Dobře, tak já si radši mikrofon.
Chceš radši mikrofon? Tak. Počkáme, až nám to tady se rozbliká. Halo, slyší nás někdo? To nikdo nečekal, takže teď ještě další technická pauza, ale už jsme tam. 3, 2, 1, halo. Už to funguje, že?
Jo.
Takže ten ti předám. A je to tvoje. Martina Zátopková.
Okay, thank you very much for the help with technical issues. And now we can go to the presentation. So ladies and gentlemen, welcome. My name is Martina Zátopková, and today I will give you a brief overview of how we scientists read the genome and some examples of what can be done as a follow-up analysis. So at first, I'd like to tell you what is genome. So I'll play you a brief video that I will comment. So genome is genome is complete information of human DNA. Most of it is stored in the nucleus, and this is what the condensed form looks like, a chromosome, but you all it's kind of strand that contains a double helix of DNA. The parts that are used to create proteins are called genes. And now we will take a look how proteins are made. So first, the DNA is translated to RNA because DNA is stored in the nucleus, but proteins are created outside of the nucleus. So this is a way how to transfer it outside of the nucleus to the correct parts. I'll give it back a bit, so you can see that it is created from 4 bases that are marked as C, A, T, and G, and the complementary strain is always created according to complementary with T with A and C with G, or T with U, which is there instead of T in for mRNA. Okay, so this is how the template is created. Then this molecule goes outside from the nucleus. It also undergoes some other modifications that allows creating several kind of proteins from one gene. Yeah, and then it goes to ribosomes, which is a protein complex that translate the RNA to the gene. So the protein. So protein is basically strand of amino acids. And you can see this tRNA, it always brings one amino acid at one side and the anticodon at the second side. And yeah. And this is very important because now I'll tell you what a mutation is. It's when the letter, okay, yeah, if one basis changes, you can see that it can completely change the amino acid that is incorporated into the protein. And if it changes, if it changes, it's sometimes not such a big issue. But for example, if 1 or 2 letters get out of the strain, it can completely change the reading frame and completely destroy the the sequence of amino acids, and the resulting gene is then completely different than what it should be. Now, why this is important? You can see the resulting strain that goes up to the cytoplasm, and the last part is like binding to the secondary structure. This is very important because the shape of the protein gives function to the protein. According to shape, it binds to other proteins, and then it works as a machinery. Okay. So this was a basic introduction. Now I would like to continue. So when we want to read the genome, first we take the samples. Usually we take blood or buccal swab. If we work with cancer, we are working with biopsy. And in the tube, by several steps, that first lyse the cells and then binds the DNA to a column. It allows us to wash everything else than DNA, and we can further dilute it and work directly with the molecule. Now, the genome of a human is huge. It has 3 billion bases, and the techniques are not able to read it at once. So we need to cut it for Illumina sequencing, and the insert size is around 150 to 500 base pairs, and then we read it from one side and the other side, and up to the resulting inserts of 100 letters approximately. There are also several new techniques like Oxford Nanopore that are able to read the longer sequence up to usually around 150,000, but the longest one was 4 million base pairs, and but it has a bit higher error rate. So in the various protein assembly studies, these techniques are combined. Okay, so for the sequence, for the Illumina sequencing, the resulting file looks like this. It's like a collection of 4 row. It's a collection of 4 row sequence where there is a sequence name, sequence itself, empty space, and quality of the read. And now you have 2 options what to do with it. At first, you can try to do assembly of a new sequence. This is usually done for organisms that don't have the sequence ready yet. And you need to do error correction first, then you need to do contig assembly, which you do by read overlapping and by the Bruin graph analysis. When you have like shorter contigs, you need to connect them with other scaffolding, and usually this is a moment where you need to use the longer reads. And then you have other steps of gap filling and polishing. and in the end you have a new sequence of DNA. So the most, I would say, most important project focused on a new sequence creating was reading of human genome. It was done in 990 to 2003. 2003 was the first version of human genome, but in 2022 was the last version done, which covered all the sequence, including the hard part. All the project cost around $4 to $5 billion, and was done on 20 people. And all the human genome now has around 3 billion bases. So this was a very important project, and each new human sequencing project uses it as a reference. Because now when we have a patient, we don't need to do the creating of the genome de novo, but we only take the raw genes, the raw reads, and map them to the reference sequence. I maybe use this again. We need to map them to a reference sequence, and we are only take a look where the specific positions differ from the reference one. So when you take at the specific position, you usually have some bases that are the same with the reference sequence, and some of them differ, and you need to put some kind of threshold that allows you to decide whether the mutation is a variant or whether it is some kind of bias. And in the end, after this basic analysis, you always end up with some amount of false positives and false negatives. This is the VCF file, which is a result of the variant calling analysis. It's basically a list of mutations with some other information that helps you to filter it. Yeah, and how to decide whether the variants are meaningful results or whether it is just artifact. That's a really hard question. At first, we have a chance to annotate it with public databases that can tell you whether the mutation or the change is causes some protein structure change, whether it is a rare mutation that is common in population and maybe not causing any issues, and really many other information we can get from public databases. A lot of this information was gained from biological tests. Okay, then you filter, you can do some visualizations, interpretation of what you found. And if you have some mutation that you suspect of disease creating, you should always do some other tests. For example, Sanger sequencing that confirms the single point mutation. You can also do testing on cell lines and do some precision medicine based on it. Okay, so now let's imagine we successfully sequenced genomes of several people. You can first do cohort studies. There are really a lot of projects in the world. These are some of them. UK Biobank and Our Future Health are biobanks in UK. UK Biobank currently has 500,000 people that were sequenced at one time point, and then they are regularly tested for presence of diseases. Our Future Health is a similar project, but it aims to 5 million people, and there are many others. So if you have a project like this, the most common analysis that is done with that is called genome-wide association studies. The principle is quite easy. You have a group of people that are affected by some disease, and then a healthy control. You can see in this picture, it is the most common scenario is that there are mutations present in both affected and unaffected controls, and you need to go through the genome step by step, each position, and test by some statistical test whether there is a significant difference among amount of people in the affected group and unaffected group. The output is called Manhattan plot. You can see this at axis X. There is each single position at the genome, and at the axis Y, there is a logarithm of p-value. So, for example, in this position, you can see that there is some region with very high probability associated with the disease. You usually choose the statistical test based on the phenotype type, and this is what usual output looks like. You always have a list of each line is each mutation, and you have the statistic outputs. So for GWAS analysis, because there is a huge amount of positions that can actually have impact at the disease development, we don't use the usual p-value 0.05, but we go to 5 times 10 to minus 8. And it is also possible to adjust the p-value even more. Okay, so this is the most common one. Of course, there are much more kind of testing you can do on such data. But then if we have a single patient, there are other tests we can do for them. Of course, we have a list of mutations, a list of diseases that are caused by single mutation that we can test by easy tests. Basic ones, we don't need to sequence all the genome, but most of the diseases is coded by multiple genes, not only by one. And then we can use output of the GWAS studies associated with specific disease, and individual outputs of genome sequencing from the individual patients. The calculation of polygenic risk score includes various variables, and we are able to say whether the patient is under risk. Of course, the fact that the patient has the mutation doesn't always guarantee that the disease will develop. It depends on various other variables like environment he lives in and so on. Okay. If we are talking about mutations, I need to mention cancer because it is specifically a disease caused by mutations in DNA. Most of them, it's never only one mutation. It's really caused at multiple places in the body, because at normal condition, each cell in your body has the same DNA, and the fact that your eyes look different than your leg is caused by the fact that that the part of the body uses different gene, but the DNA is really complete in every single cell. Now, if you get the mutations that affect the part of the genome that says how fast the cell should divide, and you have also mutations in cells that may be called how immune system should behave and other important things, the cells start to divide in extensive amount and cause the condition we know as a cancer. If we are able, you see that the during the development, the stroke has different kind of mutations, because maybe the cells that had advantage at the very beginning are overgrown by later stages. So if we are able to sequence the stroke, for example, in this time point, we are able to say whether the cells will react at different kind of treatment. This is called pharmacogenomics. So at the left, I gave you an example that is associated with cancer. This is proteasome, and it is organelle in a cell that is responsible for cutting of wrongly folded proteins. Now we have a bortezomib, which is a drug from proteasome inhibitor group, and the way how this drug works is that it blocks proteasome. Why is it bad for the cell? Because cancer cell divides very, very fast, and if it divides fast, it creates a lot of wrong proteins. Now, if you block an organelle that cuts them, they are collected in the cell, and in the end, there is so much of them that the cell disrupts, and this is how the cancer cell is like destroyed. But if we found out that there are several cells that are able to create mutation that is able to block the protein, that is able to block the blockage of this organelle, and thus the cancer cells are able to survive. So this is possible to test on the DNA level, and if you know that the patient has this kind of mutation, you can apply a different kind of treatment that will actually work for the patient. Another story from the pharmacogenomics is about one scientist who really struggled to have a baby. So she sequenced her DNA and found out that there is that she has a mutation in a gene that is responsible for metabolism of one kind of protein, and she found studies that offered a solution, and now she has 2 babies, very happy. So these are just 2 examples of how the analysis can help patients. Okay, one other interesting kind of analysis for cancer patient is associated with mutation signatures. This was actually a very easy and clever idea of a scientist who was thinking, does it, because at the very beginning you saw that the proteins are created from DNA according to triplets of 3 letters. And he asked himself a question, does it really matter what kind of bases are around the mutation? So if it is mutation from C to A, does it matter whether A and A or C are around. And so he started to test several conditions with non-negative matrix factorization, and he was really able to find patterns that are associated with, for example, with smoking, UV light exposure, some polymerase activity, chemotherapy. It is really possible to detect various kind of drugs in a stroke of patients, alcohol drinking, ionization radiation. And so I think this is really very interesting that this kind of thing is possible. Currently, we have around 100 mutation signatures. Some of them are associated with known conditions, and some of them are yet to be find. But this is analysis. This is quite widely done. Okay, one other interesting kind of analysis is about cell-free DNA, because DNA, if you have a baby or if you have cancer, it is possible to detect DNA in a peripheral blood of the human. So if we do analysis of this peripheral DNA, you can actually create a test that tells you whether the baby is healthy or whether you have a stroke and what kind of stroke, and you don't need to go invasively to the patient. Okay, so the role of bioinformatician in the genome analysis is mostly creating of pipelines that analyze the data. We use very widely, like SnakeMake, Whittle, and Nextflow tools, yeah, the very important part is to be oriented in the tools you can use and how to set them, and then you do various of other analysis. It connects from, like, you need to know a little bit of computer science, chemistry, biochemistry, biology, statistics, mathematics, engineering, and somehow put everything together. Thank you very much for your attention.
Thank you very much, Martina. We'll have questions. There's quite a few of them on Slido. So it was very interesting and people want to follow up. So starting with the most voted, how many people actually work in genome analysis field like this in A, Ostrava, and B, in the whole Czech Republic?
Oh, okay. That's interesting question. I don't know really how to answer. It is possible to study bioinformatics in Prague, Brno, and Ostrava, as far as I know. I think maybe in Olomouc as well, and other cities. And the situation surely improved from the times when I started to learn this. So I would say these days, maybe 200, but just by guessing. Yeah, there's a conference, national conference, usually attended by around 100 people, and surely there are some that did not join.
Thank you. Another question, more technical. Text files are, I would guess, inefficient for storage and reading. Are binary formats or specialized databases used as well?
Yes, yeah, all the files are usually in binary formats. We barely use only text formats because, of course, it is it's difficult, or of course the storage is not. You need to find a way how to do good storage for the big files. So we work with binary files, but I presented text files, so it is human readable.
Thanks for presenting readable text files. It was a nice read.
I can show you how the binary files look like as well.
Yeah, is there any question in the audience? If not, we can continue with the online ones, of course. Can techniques from the AI world like LLM work, like embeddings, transformers, etc.? Can you use that for working with DNA data? If so, what would be the use cases?
Okay, so surely AI affects this field as well. And I don't know how to answer this.
Okay, no worries. That's not an exam. More philosophical question. What is the most difficult part of your work?
Okay, I would say the most difficult part of the work is that you always work with probabilities. You can be never sure or actually in some cases you can be sure that what you do is 100% correct, but most of the time you work with probabilities.
Okay, so how much time, and this means either human time or machine time, is needed to analyze the DNA and say if there is a high risk of some disease?
Okay, it depends on the tool you use. So when I started to do the analysis with 22 samples, it took 1 week to calculate the analysis from the very beginning to the very end. These days, the tools improved, so it is possible to count the genome, I would say, in 1 day.
Thank you. So 2 more questions. So how do you perform error correction after reading the DNA?
How do I perform?
Error correction.
Yeah. So of course you need to double check after each step. You need to, for example, after mapping of reads, you need to check what is the percentage of mapped reads. You need to do quality check of the basic data, and you need to do all the checks that need to be done. And like my most favorite, I always prefer to check the presence of the variants by some other technique than whole genome sequencing.
Okay, and so the last question, maybe quite long one. What program or tools are you using for data processing? Did you need to? That's maybe very interesting. Did you need to develop your own tools? Did you develop any? And how much data in volume it is that you collect? Megabytes, gigabytes, terabytes?
Okay, so I did not need to create my own program. Mm-hmm. Usually you really need to be oriented in the various of programs you use and how to set them and how to do the quality check in various steps. You need to be able to make your own pipeline and put together the tools. At the very beginning, you can do it with Bash, but SnakeMake, Beetle, or Nextflow are the most used recently. And what was the?
How much data it is? Megabytes, gigabytes, terabytes?
So it is gigabytes. Yeah.
Okay.
I told at the very beginning the human genome has 3 billion letters around, and the letter and the data of exome, which is 1% of genome, is around 3 to 4 gigabytes. And I also recently worked with a specific file that contained 40 gigabytes of data.
Nice one. Okay, so thanks again. That were all questions. Thanks, Martina. It was very nice. And I guess now we have about 12 minutes for a break, so we will reconvene at 7 for the next round of talks. Thank you. Okay, so I hope you have enjoyed the refreshments. There are still some left, so don't leave immediately after the talks end. And it's my great pleasure to welcome two speakers at the same time, Alena and Emanuel from Rankacy, who will speak about data in the gaming world, if I'm not mistaken.
Yes.
Thank you.
Yeah, okay, so hello everybody. For those of you who don't know us, there is not much of you. We are from Rankacy. I am Alena, this is Emanuel, and we are going to talk about how we use Python to analyze millions of games and data. So quick overview of what we're going to talk about is basically something about us, something about Rankacy, how much data we have, how we get them, and what we do with it. Then I will do some quick introduction of our infrastructure so you better understand how the data flows through our system, how we get them, and how we store them. I will then move on to our migration from Django to Fast API, what it brought us, and what benefits we get from it. After that, Emma will continue with parsing and analysis of the CS2 games and the data. And as the last topic, we have picked up some biggest challenges and struggles we have encountered while developing at Rankacy. So a bit about myself. I have master's degree in software engineering from Ostrava. I have been at Rankacy for about 2 years now, and I am team lead of backend team there. I was previously full stack developer, but my ways from frontend has shifted because I enjoy backend now.
And I am Emanuel Dopater. I've got also master degree at VŠB in machine learning and data science. I'm currently working as machine learning engineer at Rankacy, but I spend also significant time on backend.
Yeah, so something about Rankacy. In our presentation description, there was quite misleading information about us processing only 200 terabytes of data, which is not true because as of now, we have more than 700 terabytes of data, which comes from 2.5 million games we have already seen. And if you wanted to watch it back, it would take you more than 1,600 years. So it's kind of a lot. In those 2.5 million games, we have seen more than 9 million unique players, from which there is 45,000 platform users. And daily, we retrieve more than 10,000 games, and that adds up to more than 3 terabytes of new data. And so you can imagine how the platform looks. Here is a quick sneak peek. And as you can see, there are some aggregated data, some, data from last matches, like your total kills, total deaths, your best maps and win rates, then of course your matches and match detail, and you have strengths and weaknesses which we evaluate, and then we have also 2D map which can help you replay the whole game back from all the data we collect. With 2D map is connected highlight creator, which allows you to select your best or worst moments, that's up to you, and create a video from it. We have implemented also our custom ranking system, which is a leaderboard from our selected statistics, which now are mainly AIM statistics. And last but not least, we have our own training application, which is meant to help you improve in all of those AIM statistics, right? So you can better understand the data and the flow in the system. I will go a while back and as how we started. The first setup was just on-premise setup, which we had just on local machine in our office. And it was great for the prototypes and everything, as we didn't need to have it hosted anywhere else. But as we wanted to deploy first production version, we needed to move on to VPS, which didn't mean much changes as of infrastructure, as everything was still running on one server, and it was still running as Python system services. It was not Dockerized, and that became a problem later, because as the users were growing and the data were growing also, we have hit scalability issues as the Python services were fighting over the resources. So we decided to move to cloud AWS infrastructure. And with that move, we have also made some major architecture design changes, which were basically splitting the existing services to more smaller services. And that also inspired the change from Django to Fast API, because we were creating more and more API services. But I will go back to that a bit later. So generally, moving to AWS helped us make the system more stable, scalable, and the deployment could be done individually per each service. And so you can see just a little simplified version of the system, which is just the services that are important for today. We have almost all of them written in Python, except for the front end, of course, and our custom parser, which is in C++. And the main workflow or use case in our system is basically connected to the game files, which we either collect from the users as they upload them to us manually, or we collect them automatically from the game servers. And as we process them, we store data in database and the files in AWS S3 bucket. We then move on via RabbitMQ to demo processing service. Then the parser parses the data, data analysis happens, and then the data are stored back in the Postgre database. From that, of course, users can retrieve them from through our backend. And why we moved from Django to Fast API? Django was great at the beginning, as it has many ORM and robust services, features. It has custom administration, it has inbuilt database system, and it has many features for creating APIs. But as we were growing, there was more and more code that was connecting to databases. There were more features like notifications, WebSockets, webhooks, and stuff. And the code just got messier, which can be a bit of a problem with our coding, of course, but that's for another talk. And with that, the onboarding got also a bit harder as the code was messier. Also, Django got slower for our use case as we needed customizable features. And they were quite, let's say, simple. And Django was too robust and just not suitable for our use case. So we have decided to move on to Fast API, mainly because it's fast and lightweight and modular, which just means that as we divided all of the service Django code to many services, like notifications work on as a simple standalone service, payment service which has webhooks from other services to third party, also works as standalone service and just needs simple API, let's say maybe 1-2 endpoints. There is no need for having a big, robust Django framework behind that all, right? So we have changed to Fast API. Now we have only SQL Alchemy ORM for database work. Everything is quite smooth. For running it, you need just basically one main Py, and everything is smooth as hell. Then if you want to onboard new people, they can really just help you with like 5 services, and you don't need everyone to know a lot of, like, Fast API is just pure Python. And the best benefit, of course, is faster execution and cleaner code base. So that was how we get the data, how we show them to users, and what we do. And now Emma will talk about the parser and data analysis.
Okay, so I tell you more about the component of analysis, which is responsible for processing the games. To make analysis possible, we need the demo file. What is a demo file? Demo file is a file, binary file, which consists compressed data of the game. When you are playing Counter-Strike game, the demo file is a recording. And after you finish the game, it is stored on the Steam servers. You can download this demo, and you can replay it in CS, in Counter-Strike to see how you played, or you can analyze it in ways you need. There are multiple types of demos. You can record on your own, which will be stored locally on your computer. But we are using basically the normal Steam demos where we can find most of information we need. So, as I mentioned, when you need to process the demo in way you need a special tool which is able to read this compressed data. These compressed data are in form of compressed protobufs. So, at the beginning of our development, we used open source parser written in Golang. This parser was simple, and it produced parse data. When you call the parser, it produced the parse data which was readable as JSON. This JSON was quick for quick prototypes in Jupyter Notebook, but it was not built for mass processing because the JSON nature, which is very slow when you load it, it is memory and CPU demanding and not stable. And this parser also lacked the another features because we needed to parse something other. So this was the reasons why we decided to develop our own parser. We've written it in C++, which is extremely fast. You can use it on Mac, Windows, and Linux. And the key component or feature of this parser is how it interchanges the data. With old parser, you needed to load the JSON, but this parser transfers this data via PyBind, and via this PyBind, you can access the data which are parsed in C++ in Python, and you can transfer it to pandas data frames, which are very easy in further analysis. So, what do we analyze in these demos? When you parse this data, there are basically two categories of what you can find here. One data are tick-based data. Tick-based data are basically chronological order of player and entity states. For example, where was the player standing, where he was looking, how many health does he had, or active smokes. Another category are events data. There are, for example, damages, kills, weapon fires in this game. From this data, we are computing dozens of statistics. Some are simple aggregation, like average damage per game, but some are more complex. For example, when computing crosshair placement, you need to use event data like weapon fires and tick data to obtain where the player was looking seconds ago. And I mustn't forget preparing data for 2D map because Philip will be sad, so I hope he's looking this stream. He's our 2D map developer. We are exporting data for 2D map as specially designed arrow files, which is some compromise for fast write to Amazon S3 storage and easy and efficient work on the front-end side. So, data analysis, how it started. Analysis component was very, to great extent, affected by the output data of the parser. With first parser, you needed to work with JSON. When you load it to Python, it is the native type as dictionary. This parser, as you can see it, I don't know whether you can see it, maybe yes, it was the long hierarchy that consists of information about the game. Game has array of rounds. Rounds has array of time frames. Time frame has array of players. So you can see this hierarchy is very deep, and to process it, you need to loop for all these arrays, which was very slow and inefficient and not scalable. But when our parser provides data in data frames, you can see there that I I created Python object as parser, and I parsed ticks. So, and I don't know whether you see it, but because the data, because parser provides data frames, we leverage vectorized operation. All analysis module was rewritten with use of pandas and NumPy. We vectorize every operation which is possible, and we don't tolerate any for loops. Exception has some data frames with up to 10 rows of 10 rows. So this is all what I needed to say. And because we acquired large amount, millions of demos, which are petabytes of data, we decided that we can train large AI models, mainly transformer-based. But to prepare data for these models, it is a little bit different. In our normal basic analysis, we are processing one demo at a time. But for large AI model, you need to process as many demos as possible in one batch. To do this, Pandas has some disadvantage that it is single-threaded, which means that it uses one CPU core. Polars is very similar to Pandas, but it is multi-threaded, and it also supports some lazy operation and query optimization, which makes it even more efficient to load data. For example, you don't load the columns you don't need. And another problem, another problem we need to solve was how to store this much of the data because there are terabytes. So we decided to use special packet storage, which is Delta Lake, and we have here medallion architecture, and it consists of 3 levels of data. First is bronze level, where you take the demo, parse it, and save all the data which comes from parser. Then data process to silver, where some necessary transformation or filtration is conducted, and then it proceeds to gold, where are data ready for training. Here we can drop some unnecessary columns or filter out some problematic games. And byproduct of this Delta Lake is that we have thousands of demos processed. For example, on the right, you can see a heat map. So we take basically kills from millions of demos. And we computed heat map, which tells you basically you click on some square, which is in some space on map, and it will compute you the probability where the kill can happen, and we feed it to the neural network, but we use this for visualization. So with Delta Lake, it is the matter of basically one select query and one transformation. So this is everything for analysis module, and now we tell you more about our general system struggles.
Yeah. So we picked 2 bigger struggles we have faced. One of it, or both of it, came with us migrating to AWS. First one I will talk about is scaling and message passing. As we were on VPS before, we didn't really care about scaling, or we didn't have to do it. As the user load was small, the data that were flowing through us weren't that big, and everything could run like single-threaded, right? Then we decided to move to AWS and change from Django Celery scheduling and background jobs and some database like queues we made to process our jobs and messages, and move up to RabbitMQ. We have chosen RabbitMQ because it is very easy for us to scale by the number of items in the queue. So as we found out with more and more users and more demos, we have peak hours, of course, as the players play in the evening mostly. So approximately 80% of all of our data comes in like 4-hour span. And in that time, we need to scale up all of our processing services, right? And doing that by scaling by database is possible, but doing it by scaling by queue is much easier, simpler, and cleaner for us. So we decided to use RabbitMQ. Now we have Rabbit probably in each of our service as they need to communicate with each other. And it was really straightforward and simple to integrate in Python via Pike library, right? And now in the peak hours, we retrieve demo from user. It stores data in database, creates some records, and through the RabbitMQ message queue, Rabbit message queue, it sends it to our other services, which they scale up or down based on the load on the system. And that was one struggle we faced and solved. But with that, we also came across another struggle, and that brought us another struggle as we were working in parallel. All of our code was running asynchronously and parallelly, and then some parts of the logic were fighting with each other, and we needed to handle stick terms and locking gracefully. And that is one of Emo's favorite tasks and topics, and he will greatly tell you about it.
And it was. So how to explain at the best? So I first start with the locking. We are computing many statistics, and one of them, for example, ranking, is statistics which is dependent also on the values from previous game. It should be, when you need to compute it, for example, from 30 games, it needs to be chronologically in order, because if you ignore this ordering, you can override this rating or lose it. So it is obvious that when you are processing games from the same player, this player has multiple games, you can't process it in random order, because as I mentioned, you will override the ranking. So we need to implement locking mechanism. How we implement this locking mechanism? We use Redis. Redis is very fast in-memory database. So to acquire log, you basically insert the value into the Redis. To check whether something is logged, you check whether this value is in the database. And if you are releasing log, you delete this value. So our processing pipeline looks like basically we process everything what is possible, what is independent on the other demos. Then when we need to compute ranking, we need to acquire log. When we are on the before the log section, we check whether at least one player in this game is already inside the Redis. If yes, it would mean that the demo is already processing with this player. So we will wait until the log is released. Then we obtain the log, we compute the ranking, and we release the log. We need this part is most critical in our system because it is basically the parallelization. The quicker this section will be, the more demos we can process in parallel. Okay, so we implement this locking mechanism with SIGTERM, which is correct. But because we are in cloud environment, there is some problematic inconvenience. And it is basically scaling up and down pods or parallel workers. The system which manages it depends on the traffic, how many demos are to be processed, and when there are high traffic, there will be more parallel pods, and then when there are no demos to process, it will be less. So this process is scaling up and down, and when the system is scaling these pods, they can tell some pod to shut down. And from these shutdowns, the problem arises. Because how it tells some pod to they should shut down. It will send a special signal called SIGTERM. When this SIGTERM it basically the pod is some process, and when this sig term is called, it tells to this process that it should end. It is important to the process to be able to respond on this signal, because if you are not prepared, you are not responding on them, it will just terminate immediately. And as you can see, we have log section where on the beginning we acquire the log, which we inserted to Redis, and then we need to release the log, which is deleting from Redis. If you have an idea that you can just wrap it to the try, catch, and finally block, it will not help you because the program just terminates. So the solution is quite simple. You need to react on this signal. Basically, you create some function which you register on accepting sig term, and in this function you will clean all your stuff you are processing, make database to consistent state, and most importantly, release the logs. When the system sends you sig term, you have some time to do these cleaning operations. But if you are too long, or you can just ignore the sig term, it will then call you sig kill, and on this signal you cannot react. The termination will end immediately. So this is everything for our presentation. If you have any questions, just please ask. And thank you for your attention.
Thank you very much for a very interesting talk. And there were some questions on Slido, but is there any in the audience before I switch to online world? Okay, yeah, please. Go ahead.
Okay, so thank you. So how do you deal with the deadlocks? Is it by using this sig term? Is there any action that can end in other than sig term, right? For example, it can take a long time to process the demo, right, and so on. So you have a deadlock. So
Yes.
how to deal with that?
I can take this microphone.
Okay,
We are dealing when we are inserting some logs to Redis. This log has time to live, basically. So the value is maximally stored, for example, for 10 minutes. And after the 10 minutes are passed, this value is invalidated, so the log ceases to exist.
Okay, so questions from the online world. Would you still use C++ to develop the parser now, or would you choose Rust or some other language instead?
That's probably not a question for the two of us. We haven't written the parser, but our colleague here in the audience have written it, and he can maybe tell you.
Perfect.
So my personal suggestion right now, I think that if I knew Rust, I would probably wrote it in Rust, but as of when I was writing the parser, I only knew C++. So, but generally, I think Rust is a better solution for this kinds of problems. So, yeah, I think yes.
Thank you. Another question. Sorry, okay. Is storing so much data on AWS expensive?
Yes.
How do you optimize it?
Very. And if you screw it up, it is even more expensive.
Okay, very optimistic.
Did not happen to us.
Very optimistic then. Okay, maybe a question that you cannot provide an answer for because it's a secret probably, but which models do you train on this data?
We are training transformer-based models which can predict multiple features in the game, but I am not sure what can I tell you. So we have also here CTO. So you can come us after these questions, and we can have a little bit talk.
Oh, I see. Okay, perfect.
We
So
have a whole company here.
Okay, so maybe last questions for now, and we will leave all these for beers. Would you recommend the way that you made from on-premise to VPS to AWS would you recommend that to other startups, or would you recommend to start using AWS right from the start?
I personally would not recommend starting on AWS because, well, you don't need it at the start, I would say. It is quite robust and, well, why would you? And it's expensive also. And for prototypes, you just really need the local machine, right?
Perfect. So are there any other questions in the audience? Okay, perfect.
So you mentioned that scalability is, of course, very important for you, right? Also for your queues. So I was thinking, why not something like AWS native, like SQS, for example? Why Rabbit?
Yeah, so we have been thinking about SQS, I think, and it was a decision. We have like a company that helps us with all the DevOps, and they had just said that we can choose, and the Rabbit was their, I would say, preferred solution. But I think we were thinking about going to SQS, and maybe later on we will change that.
Thank you. And now there is time for our last speaker, Lumír, who will come with some random topic that he selected.
Tak jo, jsi ready? Doufám, že jste taky ready. So, Lumír Balhar.
Hello. It's me. Oh, sorry, that's a different show. Hello, nice evening, everybody. My name is Lumír, and today I'm going to talk about some, as Honza mentioned, some random stuff. So let's close your eyes for a minute and imagine that you are a developer and you got a bug to fix, and that bug was reported by a tool that's checking some weird stuff happening on your memory, especially memory management, so-called. And you fixed that just by removing 2 lines. That was pretty easy, wasn't it? So you feel good, you delivered a bunch of story points, your Scrum Master are happy, and everything works. But you just caused damage worth millions of US and spread around the globe. And that's pretty horrible. And that might happen when you jungle with random numbers that are not so random. And we will talk a little bit about it. To understand the problem you just caused by deleting 2 lines of code in a library, you have to first understand what are the random numbers. So let's define those. First thing is that the result of a random number generator has to be unpredictable, right? To be truly random, basically. And if you ask for a number in the range, let's say, all the numbers from that range have to have the same probability to appear. So you cannot predict the result, and they have to be uniformly distributed, as you data scientists call it. It's something like rolling a dice, even though you might be surprised how easy it is to create unfair dice, really. Let's find something about it, Google it. It's really funny how in casinos they tested the dice back and forth to make sure that they are really fair. So if we get back to Python and talk a little bit about Python, What's behind the import random, you might think? And it's not applicable just to Python, but to all other languages as we know them, because all of them somewhere in their standard library has a way how to handle the random numbers. It's a random module in Python, but it might be whatever you prefer in other languages. So in the documentation, you can find a warning like that one. So be careful. This is an implementation of so-called pseudo-random number generator. We will get to it in a minute. And you should really not use it for any cryptographic purposes. Please, anything that's tied to security, use secrets module instead. All right, you might be thinking, well, random is not actually random, and that would be true. That's what the pseudo-random number generator is there for. So what the pseudo-random thingy even mean? Basically, for a lot of applications in software engineering, you need something that looks random, but don't have to be really random, but have to be fast. For example, it can be like a simple mathematical formula. You can imagine that like a mathematical equation that's taking some inputs and generate some outputs, and then take those outputs again as an input and generate something else. And even a simple mathematical formula like that can be considered pseudo-random number generator. And you might think, but the result of something like that is predictable, right? And that's true, you are right, but it's not a problem for many different applications. Those formulas, or the pseudo-random number generators, requires a seed, and that's the seed, the starting point of the whole procedure, what makes it look random. And the seed usually is provided by operating system, or it might be a current time of the machine the code is working on, or it might be even set manually. And that's it. So we have a simple mathematical formula that can generate some random numbers. We provide a seed, and because the seed can be as simple as a current time, every time we run the program, it behaves differently. It generates different results, give us different numbers. So everything looks random, even if it isn't. And that's fine. If you know what you're doing, this is completely fine, because pseudo-random number generators are good enough for, let's say, random map generators for games, or behavior of your enemies, or loot drops and everything. If you are doing some, let's say, simulations of weather and traffic and stuff like that, you need some random piece here and there. Pseudo-random generators are good enough for that. Or you need to shuffle elements in a set or in a list, or you need to generate test data and fuzzing, and all this kind of stuff. The predictability of pseudo-random number generators are not a problem at all. The benefit that they are fast is advantage you can use. And it's even helpful for debugging, because imagine a situation that you are developing a game, and the game is based on some random data. Let's say the map is generated randomly. That's what's usually happen. And then you have a bug, and you need to somehow reproduce the bug. So having a way how to set a seed and get the same random numbers generated as your user had when they were playing the game is useful for debugging. So it might also, the predictability might be also an advantage of pseudo-random number generators. But sometimes you need true randomness, and you might be thinking, when it sounds good, the pseudo-random thingy sounds good, so why I need true randomness? When you think about it, all the algorithms and protocols and stuff we use daily on the internet, like VPNs and SSH and IMAPs and all the protocol with the S at the end, use some sort of secure layer, some sort of cryptography algorithms, and all that stuff. And all of those algorithms are open source, and they are defined in some RFEs and so on. So if the algorithm is open source and you know how it works, it's the true randomness that makes the keys and secrets and all the certificates and stuff like that unpredictable. So in those cases, you really need the inputs to be truly random. And yeah, those are all the examples I already mentioned, some hashings and salts and peppers and stuff like that. All of that is defined and implemented in an open source way, usually. So you need the inputs to be random. And for that, we have something called true random number generator, which is something which is, it's not pseudo, it's true. So it's truly random. But there is a problem. Computers by themselves are deterministic machines, right? So if I say, I need you to calculate this and that, it will behave like that, hopefully, if you know what you're doing. But it's deterministic. You give it instruction, and it behaves along those instructions. So there is no way, no easy way, how to make computer to generate something truly random. So it needs help from an external source. And those external sources might be all different kinds. Everything you can imagine can be basically used. So if we stay inside the computer, inside this black box, we can use the electrical noise that can be detected on some parts of the computers and chips around. We can use the thermal noise, which means that we can measure the temperature of graphic card when playing Counter-Strike and stuff like that, and see the differences in temperature on the hard drive and CPU and GPU and stuff, and use it as a source of data, the random data. Or we can use some external device, like one measuring atmospheric noise, which is actually used for many applications. And we can use some inputs from user, like mouse movements. Those are pretty random as well sometimes. Keyboard timings, or just the timings of the packets that are arriving on your network interface. All of those data can be collected and combined and create something called entropy, and create really big pile, really big source of random. And the true random number generator takes that, basically process the data somehow, it depends on the implementation, and can provide you truly random outputs. And that's what you need for cryptography. But the problem is that collecting those data, it's not that cheap as just calculating a simple mathematical formula on your CPU. So it's slower. If you need to buy external hardware, it's more expensive, not just for computer time, but also for the actual money. And those are harder to implement because you have to be 100% sure you are doing it right and the results you are getting are random. But they are more secure, so it pays off sometimes. You might be thinking, all right, so we have something which is fast and kind of easy to implement, and we have something which is slow and hard to implement. Can we have both? Can we somehow combine those two? And the answer is yes, you can. The result of that is called cryptographically secure pseudo-random number generator. And I hope this is the last time I have to say that. So CS, PR, and G are the combinations, basically, of fine-tuned pseudo-random number generators that use true random number generators as a seed. So basically, they take, as an input for the whole sequence, they take a seed, they maintain some internal state, which is kept really secretly, and then it's fine-tuned algorithm, which is, again, well-defined and implemented as an open source. But the thing that it's based on the true random generated data at the beginning, and the data it uses, the internal state, is often reseeded again and again and again in the process of calculating the next output. That's what makes it fast enough and true random enough for the usage of in cryptographic algorithms, basically. So it's fast and it's random enough to be used in a secret way, and it's used in basically all the implementation I mentioned previously, in all the libraries that has to handle those algorithms and those processes. In Python, it's basically the secrets module, but you can think about much more libraries that are based on this thing. The best example, I would say, is OpenSSL, which we'll talk about a little bit. And a little bit is now. So what could go wrong if you think about it, and if you exchange those generators between them? It might be harmful, because some of the algorithms really need true random numbers to be effective and to be protected against attackers. So the vulnerability I was talking about at the very beginning in our short story is a vulnerability from 2008, and it happened in the OpenSSL library, but only in the Debian Linux. The problem was that Debian used Volgrind and some other software, I don't recall the name, sorry, but used Volgrind for testing the libraries they shipped as a deb packages. So in a Linux distribution, usually you take the source code from upstream, you package it in a form or deb package, RPM package, whatever, and you ship it to customers. And during the way, you can add something called downstream patches. So you can change the behavior a little bit to fit your system as a whole. You can change it a little bit to play well with other packages, and you can fix some errors here and there. You can add the support for architectures you are interested in, and the upstream community developing the software is not, basically. So you can alter the thing you are shipping to customers. And one of the developers of Debian did exactly that. Basically, they tested the OpenSSL library and all the software built with that OpenSSL library. OpenSSL, if you don't know it, it's a very well-known library handling all SSH key generators, all the certificate authority thingies, and all the security stuff around the Linux distributions are usually implemented in OpenSSL. So they tested the library, and all the libraries around, and Volgrind, the testing software, reported that there is a problem because it uses some piece of memory it should not. The problem was that it was a deliberate decision. OpenSSL uses cryptographically secure pseudo-random number generator, and the problem they had to face was what to use as a seed for that. As we mentioned, it has to be truly random. What to use to make it fast and to make it random enough. So they decided that it's a good idea to use process ID, which is small integer from 1 to, let's say, 500,000 on the modern systems. Back then, it was even smaller. So it's very small integer, and then a piece of unallocated memory. Basically, a piece of memory no process at that time in your computer use, which usually means it's full of garbage, which usually means it's pretty random. So it works pretty well. And they use that as a seed, as an input to the cryptographically secure pseudo-random number generator they implemented in the library itself. So it should be fine, right? We have a small integer, that's not that good. But on the other hand, we have a piece of unallocated memory full of garbage. That sounds random enough because the process is, writing and reading and writing and reading here and there, and nobody cleans that memory, basically. So that should work. But Volgrind reported that as a problem because, hey, you are using a memory you don't own. That's a wrong behavior. You shouldn't be doing that, really. So the Debian developer decided it's a really bad thing to do. I shouldn't use a memory I don't own, my process don't own. So remove those 2 lines of code. As a result, basically, the whole randomness of the whole cryptographic library was based only on the small integer from 1 to 500,000. Which means that every single output of that library at that point in time was 100% predictable. You can generate 500,000 of keys, SSH keys, HTTPS certificates and private keys and everything, just 500,000, and you will have all of them. So you can then, capture the traffic on the internet and try just 500,000, which is not that big number, try just 500,000 of keys, and you will 100% sure find one that fits, and you can uncrypt the whole conversation. And that was a big problem. Like, it fixed the warning, by the way. That's always fine, right? But that was a big problem. The vulnerable version of OpenSSL was deployed for 20 months, and it caused millions and millions of dollars in loss, in damage caused, because every single key, every single certificate, everything that was generated with use of OpenSSL during those 20 months of all Debian systems using the vulnerable version had to be revoked, audit it and check that nothing else was impacted and that nobody actually used that vulnerability in the meantime. So just 20 months, nobody spotted that. It was like a ticking bomb, and it was horrific, really. So that was it. So in a conclusion of this talk, can computers generate really and truly random numbers? No. No, really, without the help of some external source. It's not really possible. Computers can't help themselves, try to, as I mentioned, take the timing and take all the stuff inside the computer, like the sensors and stuff. They can do it, but the CPU, the computing unit, cannot really do that by themselves. Is it a problem? No, not really. If you know what you're doing, and if you know that developing your own security applications with only random module is a wrong idea, which I hope you do now, then it's not a problem because you know what you're doing. Thank you.
Thank you very much, Lumír. Are there any questions in the audience? I don't see any, so let's go to Slido. And the first question is, how do you achieve through randomness in isolated containers? Because, I don't know, you don't have access to some physical devices or something. How do you do that?
When we talk about isolated containers, do we mean the things traveling from China, carrying goods from Temu, or the containers, like isolated processes? Because those usually, if we talk about, because sometimes we deploy our software on submarines, so I have to always ask, and never know. So if you are talking about the containers, like isolated processes, they usually share some parts of the operating system with basically the host one. They usually share the kernel, and kernel is usually responsible for providing those informations from the operating system. So it's isolated, but not so much, like not in a sense of everything.
Okay, so then the last question, and it's probably a practical one that someone wants to use. Do you know which random generators the casinos use? Or maybe what seeds?
Well, I would like to. And if you see me traveling around in the Porsche, I figured it out, but not now, unfortunately, no.
Okay, so that were the questions. So thanks again, Lumír.
Thank you.
And I probably now should give the mic to Matěj to conclude the session. Thank you very much. You were an awesome audience, and we had 5 amazing speakers. So thank you.
Yes, exactly. So thank you again very much to all of the speakers. So just you can give again the... I'm really happy that you traveled or decided just to be here, even on short notice. I would like to thank you, PyData Prague, to come here. And in case you would like to know more about the events which PyData organizes, so just go to pydata.cz. Yes, that's true. You will see the events. In case you want to know more about TechMeetup Ostrava, you know where to go. I think it's techmeetup.cz. And last, I would like to thank you to the partners we have, because we could not have this organization and the event without them. And just to mention them, I think I'm not able to do it. Anyway, I will share it, or I will share it also on the slides, which is online, and you see it also on every of our invitation. But it's about, I would say, 10 organizations, I mean, IT companies, which basically gives us money just to do this. So thank you for this, and looking forward for next. Yeah. So there is beer and baguettes and everything. Enjoy it.
The winner. Matěj, sorry. Can you read out this question? We are looking for the author of this question.
Yeah. Can techniques from the AI LLM work, like embeddings, transformers, and so on, be used for working with DNA data? If so, what would be the use cases?
So who did that? You did. And you are the winner.
Wow. And who? What he wins? What?
The tickets for the TechMeetup.
Okay. Great.
Also.
Perfect.
You have to
So just
return.
please come to Adam and say him your email address.
Okay. Thank you.
Díky.
Aha,